Yeah, so as Randy mentioned, this discussion is really about piping arrangements, strategies on delivering the coldest water back to condensing boilers. We'll talk very briefly on what a condensing boiler is and how to apply some of these strategies. And if at any point during this you have questions, I like it to be very discussion oriented, so feel free to jump in. If you have questions that relate to a Fulton product or how this applies to Fulton products, we'll keep that till the end so that this remains non-product specific. But anything else, feel free to jump in. So we'll start off with a little bit of basics on condensing boilers, just real top-level stuff so that we're all on the same page with how we're applying these strategies. So when we talk about a condensing boiler, we're talking about flue gas condensate. So this happens on the fire side of the boiler. It's not on the water side of the boiler. So this is not steam condensate that we're talking about. And by condensing inside that heat exchanger, by turning that flue gas from a vapor to a liquid, we're regaining that energy that would normally be lost out the stack of the outdoors, right? So this gives us an additional operating efficiency. For natural gas-fired equipment, that would be anywhere above 88% roughly. But we need the right conditions to get this efficiency. So if you take this condensing boiler that's marketed at, say, 96% thermal efficiency, and it's put in a retrofit application with the same control strategy and the same water temperatures that were used with that old cast iron boiler, are you going to see that 96% efficiency? No, definitely not. So you need the right conditions to get there. In terms of the flue gas condensate itself, look at a basic chemical equation for methane, watered down basic chemistry here. So we have our methane, CH4. We combust it with O2, and we get our CO2 and our H2O as vapor, as gases. That H2O is what we're turning from a vapor to a liquid, and during that phase change, we recover that latent heat, and that's what gives us up to that 12% efficiency gain that we could see inside that boiler. But to get there, we need to cool down the water coming back to that boiler, the return water. You get that steel or whatever material that boiler is made of cold enough, and just like a cold soda can outside on a humid summer day, you get a layer of moisture forming on the surfaces. And then that heats up the steel, which then in turn heats up the water, and you use it to heat your building. So the phase change has to happen inside the heat exchanger itself. If it happens somewhere else, say in the stack or outside, you're not actually making that available to your system. This just gives you a little bit of background on why piping strategies can affect the efficiency of a condensing boiler. So we want to get that return water temperature as cold as we can possibly get it, right? There's three main keys to gaining that efficiency. By lowering the return water temperature, we create more condensate. We're better able to quench that vapor into a liquid, and our efficiency rises. The supply water temperature actually has a pretty negligible effect. So that return water is what we're really interested in. But in terms of the controls, we're usually looking at our supply, and we're often ignoring the return that's coming back. Maybe it's looked at in the design day, but as soon as we get outside of that condition and part load conditions, things change very quickly as the load changes in the building. So we're going to look at some of that today. The other part of that is firing rate, or the modulation. In a modern boiler, we have a high fire and a low fire, and we have what's called infinite modulation, where we can turn down the gas and the air to lower the firing rate at an infinite number of points. And this is called load matching. We're matching what is being taken out of the system by what's being put in by the boiler. And finally, the control strategy. The controller that's sequencing these boilers and controlling the burners, it should be designed specifically for condensing boilers, even better if it's for that particular piece of equipment, because every boiler has different best operating points. And a condensing boiler has a completely different control strategy from a steam boiler or a Scotch Marine style fire tube or even a cast iron. Any questions at all so far? Pretty standard stuff that I'm sure many of you are already aware of. Next, we'll go into the piping strategies. So this is the main core of the presentation. I'll spend a few minutes on primary, secondary, and what that means, and then talk about primary-only designs. So primary, secondary, it's very common everywhere in North America. And the idea here is you're decoupling your system loop from your boiler loop. This is often done with two closely spaced T's, but there's other methods too, like buffer tanks, hydraulic separators. A hydraulic separator is basically an air and dirt removal tank that also decouples the loops, so there's 4 connections instead of 2, like a standard air separator. But the two closely spaced T's is probably what you see most often, right? Mostly because of cost. It's the easiest, it's the lowest cost method of implementing it. So we're preventing the flow in one circuit from interfering with another. As the variable speed pumps, if they're used, ramp up and down as valves modulate or open and close in the system, the boiler's not seeing that change in flow that's impacting the system. It's not seeing that change in differential pressure. So why is this used? Well, it's used to protect the boiler. In a traditional non-condensing boiler, it's used for temperature control primarily, but also flow control. You want to make sure that your return water temperature is high enough in a non-condensing plant so that you're not condensing in that boiler. Flue gas condensate is slightly acidic. If you begin to condense in a cast iron or Scotch-Brine style boiler, you're going to be replacing tubes or sections over time as it corrodes away that material. So typically the designs would be 140 Fahrenheit minimum, but usually you would see 160 return to 180 outlet. And that gives you enough of a buffer where if something goes wrong, you're not going to condense inside that boiler. In modern systems, the reason that primary secondary is used is because many condensing boilers out there are low mass and low volume. They have very thin materials. They're water tube type boilers, maybe a couple gallons of water. And if you imagine a water tube boiler with rows of coils, you have these little coils no bigger than your pinky finger, and the water travels inside of this. You have several feet of coils going through that boiler, and then a temperature sensor downstream on the outlet header. And if you didn't have enough flow, that temperature sensor says, okay, burner, keep firing. We need more heat. We need to get this temperature up. But without flow inside those coils, that water is actually boiling. And that's where the boiler starts to dance on the housekeeping pad, and it tears itself apart and begins to leak. So in low-mass boilers, we need to ensure that there's enough flow so that we're not boiling inside that heat exchanger, because these are hot water products, hydronic products. But we also need to protect it from a high flow condition where our velocities get so high we're actually eroding the heat exchanger. Any questions at all? No? And this is what a typical primary secondary layout of a single boiler looks like. I mentioned the closely spaced T's earlier. These are the T's right here. A typical industry standard is less than 4 diameters between the T's, but depending on who you ask, that might change. The idea is you just want to get them close enough together where the pressure drop in the pipe from this T to that T is negligible compared to the pressure drop from this T all the way through the system and the zones and all the way back to the other T. And the idea is the system pump, often called the secondary pump, that pushes flow through the system, actually this way, out to the system where it's the heat is given to the zones and warms up the zones. And it comes back a little colder, mixes with water from the boiler to heat up a little bit, and goes back through. The other pump we have is the boiler pump, the primary pump, and that's going to push flow through the boiler's coils where it heats up, comes out at a higher temperature, and mixes with the water coming back from the system to heat that up. So you always get some kind of mixing at some level between those T's to heat up the water going back out to that system. And we can expand that out to a multiple boiler plant, because many of the plants that we deal with today are multiple boilers, modular plants. In this plant, we have a 4-boiler system. We have a common return header coming back to the boilers with reverse return. This helps balance the flow between each boiler. You can also use balancing valves to get this effect, but this is just shown in kind of an ideal layout. And then we have a dedicated pump for each and every boiler with a check valve for each and every boiler. When a boiler has a demand and its burner turns on, it starts to purge. The pump comes on with it and starts providing flow through that boiler, which then mixes through this common supply header, mixes in the T's, and comes back to the boiler where it's heat up again. And then the system still has the pump package to provide flow out to the system. So you'll notice when we get to these bigger and bigger plants, we can have a lot of piping fittings, a lot of pumps because we need a pump for each and every boiler that's there. So it can become complicated. It can take up a lot of space in the mechanical room. I mentioned a hydraulic separator earlier. This is a cutaway of a hydraulic separator. Just makes the visuals a little easier than looking at closely spaced T's. So what we're looking at here is air and dirt removal. So the dirt at the bottom, air at the top. We have a port coming from the supply of the boiler, so hot water from the boiler, cold water going back to the boiler's return connection, hot water out to the system, and then cold water back from the system. And in the primary secondary layout, we can have three different situations that will occur. And the first one here is balanced flow. This is where our boiler GPM and our system GPM are identical. Is it practical to have this happen in the field? Is it achievable? It's very difficult, but if you had constant speed pumping, you could probably get there or get very close. But in most modern systems where you have multiple boilers and variable speed pumping and modulating zones, the second anything changes, this no longer applies, and you have some kind of mixing going on, right? So this is ideal in a condensing boiler plant. We're getting our coldest water back from the system, T4, right back to the boiler, keeping our return water temperature as low as it possibly can be. And we're also getting the hottest water temperature from the boiler out to the system. But again, it's very difficult to actually get this implemented in the field. The second situation you can run into is where your system flow rate is greater than your boiler flow rate. And what's happening here, you can see the cold water coming back from the system is being pulled back up and mixed with the hot water supply from the boiler. So T2 going out to the system is lower than our T1 from the boiler. So this is what our set point is going to be looking at, right? That's what the system is asking for. So what does the boiler have to do to T1 to meet that T2? Right. The burner starts ramping up. It has to supply a higher temperature. In condensing boiler plants, the safety lockout's usually set to either 200 or 210. And they have about a 5% error. So around 190, you're risking a high limit trip. And a high limit trip, for anyone that's not familiar, is where the facilities guy has to go down to the boiler room and hit a little red button or a reset button on that panel. It's a manual reset lockout. And if that happens over and over and over and over, that facilities person's either going to do one of two things. Make a phone call and won't be too happy, or mess with the safeties and they're no longer providing the safety functionality they're supposed to. So it's good to try to avoid that manual reset high limit trip. The third is by far the most common. And that is where your boiler GPM is higher than your system GPM. And the reason why this is the most common is our system pump is usually variable speed in most modern systems today. But what are our boiler pumps? Almost always, right? They're almost always constant speed. That's not always the case. But in the majority of systems that we see, and I'm sure that you see, those pumps don't turn down. In the majority of the year, we're operating in part load condition. So this pump is, if it's a 3-to-1 or 4-to-1 turn down pump, it's bottomed out the majority of the year. So you have multiple boilers probably running at low fire. Their pumps are providing full flow, but the system pump is turned down. And the effect you get is you're pulling that hot water that the boilers are supplying right back in to the boiler's return connection. I mentioned earlier in a non-condensing plant, you use primary secondary for temperature control. This is exactly what was done. You size your boiler pumps to have a higher GPM so that you pull the hot water back and you keep those boilers from condensing. But in our condensing plant, where we're trying to maximize the efficiency and cut the customer's fuel bill, what is this doing, this T3? Right. Or at the very least, it's raising the temperature and you have less condensate, right? Yeah. It's lowering your efficiency. You have to burn more fuel to get the same output to your system. And this can be avoided by using variable speed pumps on the boilers itself. But that adds cost, it adds complexity. There's a finger pointing of who's going to control it. So then that brings us to variable primary. And are there any questions on primary, secondary before I go to variable primary? Good? Okay. So what is variable primary? It has a couple different names: primary only, direct return, full flow. But the general principle is the same. We eliminate the boiler pumps. We eliminate the closely spaced T's and the buffer tanks, the hydraulic separation. We get a direct return back to the boiler and direct supply out to the system. We can get rid of the heat injection loops and all those other components. The last 2 points here are big. So the coldest water temperature is always delivered directly to the boiler return water connection. You're eliminating all the mixing that happens with primary, secondary. So you're guaranteeing the coldest water temperature, whatever it might be that's coming back from your system, is going right back to the boilers. So you're maximizing your thermal efficiency on that side. And then you're also eliminating mixing on the supply side. So boilers no longer have to supply a higher temperature that's going to mix down out to the system. So you're reducing your risk of high limit trips. And this is what it looks like. This is really as complicated as any hydronic boiler plant piping needs to be. Very simple. We have a header for reverse return, or again, you can use balancing valves to get the same effect. And the water comes back from the system to the boilers, goes through a boiler, it heats up, comes right back out in the supply header, and our system pump or pumps push that water back out to the system and through the boilers. Very simple arrangement. The design is easier, the installation is easier, the maintenance is easier. One really important thing to point out here are these motorized isolation valves. And those can be installed on the supply side, on the inlet side. Doesn't matter, just not both, because the water will find a way out through the safety valve if it's on both. One or the other. But the idea with those valves is when a boiler is idle, you don't want to provide flow through it. Just like in primary, secondary, you shut off that pump when that boiler is idle, the valve will force the water to go through only the active boilers. So why do we care? Well, for one, if you're sending hot water through a boiler that's not actually firing, and you have a tall chimney going up inside that building, what does hot air want to do? And what are you going to get through that boiler? Draft, right? So you're actually going to be pulling the heat out of your system, just sending it out into the atmosphere. And any boilers that are running, now they have to go up a little bit in their burners to make up for that temperature loss. And depending, it can be pretty minor, but you are losing heat, and it's easily avoided. From a controls perspective, though, what it allows you to do is eliminate a mixed temperature. I'm going to jump back one slide. If we did not have those valves, and we're setting up this primary-only layout, let's say we only have one boiler running. We have 100-degree water coming back, and we want 140 out to the system. So we have 100 coming back. The last boiler is running, so these three are idle. We have 100 going in and 100 going out, 100 going out, 100 going out, and then this boiler is providing 140, but then downstream, our temperature is much lower than 140, so the active boiler has to supply a very high temperature water, which might exceed its high limit, often does. The more stages you add, the higher that water temperature has to be, and then it'll lock out. Drops out of the sequence, boiler 2 comes on, same thing happens, that locks out, goes all the way down until every single boiler is on its safety alert. And the facilities guy is scratching his head why every single boiler is locked out in the middle of October when they don't need much heat. And that's why, is because those isolation valves, or the lack of the isolation valves, is causing a mixing temperature. In a 2-boiler plant, you can sometimes get away with it because the effect of mixing is less. Yes?
So when you bring a boiler on, you open that valve?
Yep. I would recommend just 2-position open, close.
And how do you account for what the pump is?
So the pump is going to be variable speed, typically. And as that valve closes, it's going to affect the differential pressure. So that pump, if you're using differential pressure control, is automatically going to speed up or slow down based on that. If you're using differential temperature control, which I'll talk about in a little bit, yeah, a little bit, but it's okay. Yeah. In the next couple slides, I'll talk about the high volume design. But the pressure drop through the boilers in these fire tube type boilers is usually so negligible. You're looking at a couple feet, versus what's going on in the system, that by closing one boiler, the impact is usually pretty small. And if you're closing a boiler, that means your system has less demand. So the zones out there should be closed down more too. So it usually works together. Those pumps will be at a lower point because you have less demand in the system. Those valves are closed. So fewer boilers will have an open valve. Yeah. Stealing my thunder. It's okay. No. No, it's okay. Jumping ahead. No. Here you go. Here you go. No, it's really important though. So if we don't have a bypass, we need to provide flow, right? This last point here, we need to leave a lead valve open to provide a path of flow. Otherwise, you're deadheading that pump. You can't monitor your system temperatures. It's just a controls nightmare, like you said. So whatever control is being used, whether it's the BMS or the boiler panel controller, it has to be able to keep that lead valve open. It also needs to be able to do a time delay close on these valves, because when you shut off a burner, you still have maybe a couple thousand pounds of steel, and that heat needs to go somewhere. Why not make it available to your system? So you keep that valve open either on a time delay, or what some modern controls are doing now is a differential temperature monitoring. So if you're looking at your system differential temperature, because you know this temperature here at return, you know this temperature here at supply, and the boiler has its own internal sensors, you can monitor those and watch as that delta T decreases when the burner shuts off. When it gets down small enough, say 5 degrees, go ahead and close that valve because you have pretty much all the heat out of that heat exchanger. And you're just maximizing the amount of heat and that fuel you burn that you're putting into your system. Just one of those little tricks that you can do versus just throwing 5 minutes at the valve and calling it a day. To get the heat out? It depends on the mass of the boiler, your system temperatures, your glycol. I mean, there's just so many factors. But low mass, less than a minute, 30 seconds to a minute. A high mass, 5 minutes maybe. Yeah. Also depends on your outdoor temperature too, because if you're out in Minnesota and it's negative 30 degrees, and you go through a 1-minute purge, that sucks a lot of heat out of that heat exchanger. Which one's the lead valve? Is it change? The control should rotate. It should. A good control will rotate the lead boiler. It'll rotate the whole sequence. So it should reorder all the boilers based on cycles and run hours versus just assigning one boiler a lead and having that boiler start each time, because then you'll see 30,000 cycles in this boiler and 10 on this boiler. Yeah. Yeah. And then as soon as you have a demand, that valve's already open. so the burner just starts right up. Yep. Good question.
So the BMS control those valves?
Could. It depends on whose package is being provided and what's written into the specification. Typically, a boiler controller will control the valves because then nothing gets out of sync. But yeah, because the boiler knows when the burner has a demand. But you'll see some where the BMS is controlling it. Same as a boiler pump. Sometimes the boiler controls it. Sometimes the BMS controls it. Why use variable frequency drives? Probably all very familiar with these. They're used in the majority of hydronic systems these days. But the whole idea with a VFD is we can control the speed of our pump, control our GPM. We design for the worst case scenario, that coldest day of the year, but that's usually only a couple days out of the entire heating season. And the majority of the time, we don't need all that flow. We don't need all that heat. So we can lower the speed of that pump, decrease the amount of kWs we're consuming. And then it also gives us another advantage. When we decrease the flow, we can better maintain a delta T, which keeps our return water temperature down where we want it. If we have a constant speed pump and those boilers are down at low fire, you might only see 2, 3, 5 degrees delta T across that heat exchanger. You could actually bring it out of the condensing mode when you should be fully condensing, in the October, April, May type months. The typical turn down of a variable frequency drive is 5 to 1, and even that's kind of pushing it. What do you typically see for VFDs? 3 to 1, 4 to 1, pretty common, usually. So unless you stage pumps, you bottom out the pump far before you bottom out your boilers. Because even in a 5 to 1 turn down boiler plant, let's say you have 3 boilers, you have 15 to 1 turn down in your boiler plant, but only 4 or 5 to 1 turn down in your pump. At some point, your delta T starts to decrease because the flow can't go any lower. We'll talk about that in a little bit too, in the design portion. So when can we use primary only? Well, just like some other equipment, if you've used primary only on chillers, you do need the right type of boiler to do primary only. And this would mean a high-mass, high-volume boiler, a fire tube type boiler, where the gases travel inside of the pipes or the tubes and the water surrounds it in a pressure vessel, versus a water tube where the water travels inside the tube and then the gases surround that in a jacket, what it's called. So it's the opposite effect. You'll see gallons of water, in the hundreds instead of 5 to 10. And because we have so much water volume, and because it's a condensing boiler made with stainless steel or another material that's resistant to condensate corrosion, we don't have a minimum water temperature requirement, and we'll have a very low water side pressure drop. And this is important for sizing your pumps, because if the boiler has a very, very high pressure drop, and that pump needs to get very large to overcome that, you might be spending a lot of money in electricity just to run those pumps to set it up in a primary only fashion. And then some of those savings on the gas side are going to come right out on the electrical side. So what are some advantages of high volume? Well, you're less resistant to things like erosion, scaling, changes in flow. If you think about a big tank, like a residential water heater, that doesn't need any flow to operate. That's because it's just a big tank. It's going to heat up the temperature and it's going to turn off. So the more water that you have in a boiler, the more or the better able that boiler is to tolerate low flow conditions or even no flow conditions on some boilers. And then advantages of high mass. When we say high mass, I'm referring to the steel content of the boiler, how thick are the materials, how conservative is the design. You can look at the dry weight of the boiler to get a good idea of how much mass you're getting for your dollar. But if you have a conservative design, you're less likely to have cyclic fatigue, thermal shock problems, premature failure. It's going to last longer. Just like anything, built with thicker materials, it's more resistant to changes and has a wider variety that it can be applied to. And what are advantages of this type of design, of primary only? Well, we eliminate all the boiler pumps. We eliminate all the piping and some of the controls headache that goes around or along with mixing temperatures. So if you're a consulting engineer or a designer, it makes your life a lot easier. If you're a mechanical contractor, you have a lot less to install. You don't have to weld all these additional T's and put in check valves, strainers, and pumps. If you're an architect, well, boiler plants keep getting bigger and bigger and bigger, and we have so much mechanical space to work with, it doesn't matter, right? In our experience, it's getting harder and harder, and the boilers keep getting smaller. We have wall-mount boilers now and vertical platforms that don't take up. So this will eliminate all that additional. Any questions at all on variable primary before an example? Okay. So this example system, we have some givens. So we're going to cut right through the difficult design stage of sizing up a building and determining the loads. And this is what's given to us to size and design our boiler plant, our hydronic system. On our design day, this building has a 3.6 million BTU an hour load. And then on our mild day, so our spring or fall day right before our warm weather shutdown temperature, we have a 400,000 BTU an hour minimum load. We're designing the hydronic system for 30-degree Fahrenheit differential temperature. And we're going to select 3 high-mass and high-volume boilers, condensing boilers, and put them into a primary only setup. These will be 2 million apiece input, and that gives us an N+1 design in terms of the output. So if we lose any one boiler in that sequence, we can still provide all the heat we need to keep that building comfortable on the design day. Now, sometimes that's overkill, but depending on the design, that may be required. So in this example, it is. Some high mass and high volume boilers don't actually have a minimum flow requirement because of that large volume of water. So this doesn't mean that you can put 1 GPM through a 2 million BTU an hour boiler and keep your building warm. But what it means is you're not going to hurt that boiler. You're not going to have a leaking heat exchanger. But you're not going to heat your building. So we need to have a minimum flow for that system and a maximum flow for that system. And it depends on a number of factors like our glycol percentage, our load, and our delta T. This last point here, heat should be consumed at the same rate it is delivered. So we are going to assume that our building loads match what our design calculations are, and look at our boiler outputs to match what the building load is. And we do this with the Q equals MCP delta T equation. I'm sure many of you have seen this many, many, many times. But what it is our heat load in BTU an hour, our mass flow rate in pounds per hour, and we're going to convert that to GPM, a volume flow rate, our C sub P, which is the specific heat of the fluid. We're going to use water in this example, no glycol, so we're going to assume it's 1. It drops out of the equation. And then our delta T in degrees Fahrenheit. And we can simplify this through the conversion to GPM to flow in GPM is equal to our load over 500 times our delta T. Kind of the shortcut method to determining our flow rate. On our design day condition, we really just have to plug in the numbers from that design. We have our 3.6 million BTU an hour, and we have our 30-degree delta T. That gives us a design flow rate of 240 GPM on that coldest day of the year. So that's what our pumps need to be sized for at a minimum. And then determining our minimum flow. And we want to look at all the zones in the building. What is our heat loss going to be right before we get into warm weather shutdown? And we get our 400,000 BTU an hour, plug it into the equation, and we have a 27 GPM minimum flow rate. That works out to around, I think it's about an 8.5 to 1 turn down for that system. The controller is also going to use an outdoor reset schedule. Outdoor reset is where it's a concept where we lose less heat to the outdoors on our more mild days. So we regain less heat from our terminal units or our radiant floor or coils. We can lower the temperature in the hydronic loop to regain less heat from those coils and terminal units, and therefore decrease the return water temperature going back to the boiler, which increases the efficiency. And the majority of the year we spend in these mild days, so the majority of the year we should be condensing. But we can still provide that hot water that's required on the coldest day of the year. So in this selection, we need 180-degree water when it's 0 degrees outside, and we need 100-degree water when it's 50 degrees outside. And that's the supply. So our return temperature should be 30 degrees less than this throughout the year, if we can maintain that delta T. Then we design our boiler plant. This just looks at basically the mechanical space. We have 3 high-mass, high-volume condensing boilers, set up reverse return with motorized isolation valves. We have return and supply temperature sensors, and we have a variable speed pumping package. And we expand that out to the entire hydronic system. We have multiple zones with modulating valves to control the flow through those zones. We have a bypass at the furthest point in the system, so if these close down too far, we can crack this bypass open and maintain a flow through the system to monitor temperatures and prevent that pump from deadheading. And then a sequencing panel that's controlling our boilers, controlling the isolation valves, monitoring supply and return temperatures, controlling the pump, and monitoring differential pressure, while feeding all that information back to the building automation system. A very traditional way of controlling the pumps is by differential pressure. The pressure sensors are usually far out in your system at the furthest point. And the idea is as these valves open and close or modulate down, our differential pressure starts to increase. And the controller will tell those pumps to slow down. But if you think to that Q equals MCP delta T equation, is delta P in that equation at all? No. So what is delta P telling us? It's telling us the valve position. But if you have a zone that's a gymnasium and another zone that's an office, and they have pretty similar pressure drops, you're not really going to get an accurate representation of what's going on in that system. So the controller here is looking at differential temperature between the supply and the return sensors. And we know our supply temperature because it modulates the burners to give that supply temperature based on the outdoor air. But if our return temperature is creeping up and creeping up, what do we know is happening with the load in that building? Right. For some reason, that's decreased. So what can we do with the pumps if the differential temperature is going down? Yep, slow them down. Get that differential temperature back where it needs to be. And if you're implementing a delta T logic on the pumps, you can also do what's called indoor reset. So already controlling outdoor reset and lowering the set point return water temperature of outdoor temperature. But if we have to slow down our pumps further, we can actually drop that supply temperature a little bit to get the return even lower. Because for whatever reason, the building has less load than what it was designed for. Maybe it's full of people, there's a convention, there's computers, there's the sun shining. For whatever reason, our load dropped. So we don't need as hot of water. Now we want to make sure that no valve goes full open and doesn't get enough heat, so the controller should be able to at least get feedback from those valves to make sure that none of them go to 100%. while still lowering the temperature, because you need to keep all zones satisfied, right? If we look at this on design day, we have 3 boilers, and all 3 of them are running, and they're running at 70% input. But we could also do this with 2 boilers at 100% input. But if you remember back, condensing boilers are more efficient at lower firing rates. So if we can operate multiple boilers in parallel instead of 1 boiler at high fire, we're actually more efficient by several points, and we'll save the customer on gas or propane. So we're running all 3 boilers at 70%. All 3 valves are open. We're supplying our 180-degree water. We have our 30-degree delta T, so we're getting 150 back. Our pump is providing the full flow at 240 GPM. And then this is just a breakdown. It's chosen arbitrary based on the concept here. Every zone is open. It's getting the maximum amount of heat per design condition. But then we turn the system down. The boilers are turned down, the pumps are turned down, the load drops in the zones. And as those valves start to close, they're throttling the system. And our system curve, it actually shifts a little bit on that pump curve, goes to the left. Just like closing down a throttling valve. But at the same time, we're modulating a VFD down. So if you were to not throttle and just control VFD, you would go down selection. With this VFD and this pump curve, we're able to meet the 240 on design day and the 27 GPM on our mild day. So on our mild day, we only need 1 boiler at its minimum firing rate of 20% input. We're supplying 100-degree water with 70 degrees coming back. Only a couple zones are calling, and our bypass is cracked open to relieve some of the pressure on the pump. Any questions at all?
What's your temperature range for condensing? I know it's not like maximum.
So these are just kind of chosen as an example, but if you want to condense in that boiler, typically it's around 135 to 140 degrees Fahrenheit for natural gas as a return temperature. When you get above that temperature, you're not really condensing anymore. And then the further you go down from that 135, the more condensate you create and the higher your efficiency. There are other factors involved, like the type of burner and the turn down and that sort of thing. But general rule of thumb, if you're under 135, you begin to condense. So the colder you can get that water, the higher the efficiency. Yep. But a key to remember is this here, where let's say this building required 180-degree water because it was a retrofit and they only had so much surface area to work with. That's probably only going to be a couple days out of the year when it's really cold. And that's fine if you're not condensing a couple days out of the year, because the majority of the time you don't need this much heat and you lower that water temperature and you are condensing. A couple of examples of what not to do. The names have been changed to protect the innocent. So this is the example of no isolation valves. We have 1 boiler running, 2 are idle. This is only a 3-boiler plant, which is pretty common these days. And we're looking for 160-degree water. We have 130 coming back. But with no isolation valves, the way the math works out, this boiler has to supply 220-degree water in order to meet that 160 downstream. And I mentioned earlier, condensing boilers, they lock out around 200 degrees typically. So somebody's going to be going down to that room and hitting the little red button. Another here. Now this It may work. It's primary, secondary, where each has its own leg off the main system loop. But we have a big distance between the return and the supply. And depending on how long this pipe is, we might not get proper hydraulic separation. It may work, but it's best to avoid this. Get those T's as close together as possible and common the return and supplies. Now this one is a controls nightmare. This is primary, secondary, and series. And really the only time this makes sense is if you have a hybrid plant with a custom designed control strategy to control it and control it properly. But putting in a standard condensing boiler plant and daisy chaining them, there's usually one temperature sensor downstream, but you have your cold water coming back, it heats up a little bit, heats up more, and then this boiler is probably going to trip out on high limit. You're just going to have, your burner should be operating at the same firing rate, but in this they may not be. You're going to have lockout problems and other issues. Lastly, this one is, it's hard to really to pinpoint, a cut and dry whether this will cause problems or not. But in general, if you have a very large system with a lot of water volume and you have a bypass valve right in the boiler room, you may have control issues. So this was used for many years on cast iron direct return systems where you weren't doing primary, secondary, but you were non-condensing. And the bypass valve would be used for temperature control. So you'd circulate water here to keep the temperature up. Well, in a modern system with condensing boilers, because they have modern PID logic and it's dialed into the size of the system, if you have a 5,000-gallon system and you have a 45-minute reaction time, then all of a sudden you crack this valve open in the boiler room and go from 45-minute reaction time to a 30-second reaction time. That controller on the boilers isn't going to react in time, and the boilers will just trip out at high limit. So typically, it's good to have that bypass valve at the furthest point in the system to act as pressure relief if all the zones are closed or closed down too far versus used as temperature control. And that is it. That is the whole presentation. Any other questions? Yes. Yeah.
You have that pressure bypass basically tail in the system through that pressure.
Yeah.
Why not just tail in the system, put a three-way valve instead of a two-way valve, and it eliminates the pressure differential bypass? Why put in the bypass valve? Because the advantage to that is going two-way valve.
No, I've seen three-way control valves used many times. That's certainly an option. If you were to use it modulating, you could, but it sometimes becomes difficult to dial it in because that modulating valve might fight the pressure that the pump is based off of if you're using differential pressure for your VFD. And it's kind of like pulling levers. Your pump is going to ramp up and that valve is going to open, and they're just going to bounce back and forth. Yeah. Slide 32. Yes.
So, we're connected to that one now. Is that
well, this is, instead of just drawing a line to each one, it's just simplified. Yeah. Got lazy. Yeah. It cleans up the diagram. It got a little messy with arrows on all of them. It could be a building control system or a boiler control system. Could be either.
On a small system, the boiler have the ability to do controlling that UPD. Is that? I didn't want to jump in.
Oh no. Okay.
Is that UPD controlling? And obviously, is that also integrated into control of the motorized valve?
It depends on which manufacturer. So some manufacturers don't have the capability to do this, and some do. You can probably guess which manufacturer does, but Yeah. Yeah, if you have the integrated panels, which many boilers do, it's very industry standard. The integrated panels will control each of the boilers and usually the valves of the pumps. But in terms of system control, like VFD pumps, the integrated controls usually will not have that capability. Typically, you'll need a standalone panel or a pump control panel with VMS to be able to do that. Yes. Sorry. Yeah, so that's a very, very good point. So when should you kick on the second boiler is the question, at what firing rate? Well, that will depend on the minimum firing rate of that boiler. And with most condensing boilers, they're more efficient at low fire. A good control package will actually raise the firing rate of the first boiler slightly until it equals 2 boilers at low fire, and then bring on the second boiler and drop the first one down to meet the in-between loads. Otherwise, if you turn on one boiler and you bring on a second, but that load is in between the 2 stages, that second boiler just cycles on and off constantly. Which most integrated controls will just turn on the second boiler, bring them all on until every single one is on, and then modulate them in parallel. Typically, you'll need a standalone panel that has the logic to bring the first one up a little bit. Oh yeah, as many boilers as you can run, it's best to run more equipment. Now, if you have really high electrical rates and you have a 5 horsepower blower, it might cost you more in electricity than it does in gas. If your gas is 30 cents a therm like it is in some areas of the country, and your electric is 22 cents a kilowatt hour. But in most places, that's not the case. So it usually makes more sense to run as many boilers as you can at the lowest firing rates. Yeah, it's a good question. Yes?
You base this on a 30-degree delta T. Is that typical, or is it
Yeah. So the question was, is a 30-degree delta T typical? I would say it is. Most systems are between 20 and 40-degree delta T. Usually you don't see much above 40 because most have air handling units and coils, and it's hard to get a selection above a 40-degree delta T. Unless you're in a process application or snow melt, radiant floor, usually you won't see above 40. The 20-degree delta T is used most often in traditional systems. And the reason why is they needed that 180 to 190 degree water. And by choosing a 20-degree delta T, you don't really risk condensing in that boiler. A lot of newer systems are starting to move to bigger and bigger delta Ts, but they're often limited by the coil size that's available. And at some point, the coils will just get too big and expensive, and it's not practical anymore. So if there's any consulting engineers here, do you have any experience on what you're sizing systems around in terms of delta T? 30? 30? Yeah. Yeah, I find it's pretty typical to see 30 or 40. Okay. Well, thank you very much for your time. I appreciate it. I appreciate the invite out here.